I want to talk about equivalent resistance. When we talk about equivalent resistance, it means we've got some resistors and they're in this big combination, and it may be a big ugly combination, or we may be talking about not necessarily resistors, but the resistance of some objects, machines or something like that in their devices. Anyway, we've got all these resistances in weird combinations, and we want to be able to replace them with an equivalent something. I can take all these out and put one in there and it would have the same effect. And one of the reasons you want to do that is because it makes analyzing circuits a whole lot easier. Okay? So I'm going to start out conceptually, after the bell rings, I'm going to start out conceptually with one resistor. And that one resistor, remember what a resistance is. It's how hard it is to push charge through it. So we would have some sort of electric field over that and charge would run through. I'm not going to be really talking about Ohm's law in this. That, for what I'm teaching this year, is lying in the future. But if I have this resistor there, what happens if I add another resistor? Well, it depends on how they're added. So in other words, if we think of charges being pushed through that way, what would make it harder to push through those charges would be if I add another resistor on the end of that, right? No way that's going to be able to make it easier to push charge through. It's just going to make it harder to push charge through. We use an analogy an awful lot of traffic or water. If I have a little tube that water's got to pass through, and then I put another little tube on the end of that, it's going to make it that much harder to pass through. Let's say we have a construction site, it makes it hard for traffic to get through. Having a second construction site is going to make it harder for charge to go through. So if this is R1 and I add some R2, well, I can tell that if current flowed with some ease before, current is going to be smaller now. How much smaller depends on these things. So conceptually, when you put two resistances together and the charge has to go through both of them, there's going to be less charge flow, so the effective or equivalent resistance is going to be bigger. So here's current flowing through a single resistor, and you can see the arrows indicate the direction positive charge would travel. We know that electrons would go the other direction, but current is defined as the direction of positive charge flow. What happens if we add another resistor in line with the first resistor? And you can see that less charge is flowing per unit time, so there's a lower current. So if you have two resistors in series, where all the current going through one has to go through the other, there's a larger equivalent resistance. And in fact, we call that series. Series resistance is when whatever goes through one has to go through one other. Okay, it can't split off. We can't have a resistor coming off here or some other path coming off here. Whatever goes through one has to go through the other. And if that's the case, then the series equivalent resistance, you could write it as R equivalent, or I'm just going to write it as RS, is equal to the sum of those two, R1 plus R2. And in general, if we have more than that, the series resistance is just the sum of all the individual resistances in series. Again, I can't use that if there's two resistors there and I've got another resistor over. You can't do that. Okay? These two are not in series because charge that goes through here could come over this way or come down there. And remember, the definition of series is whatever goes through one has to go through the other. So if you have series resistances, it's trivial. You can add them together very, very, very easy. Okay? A slightly more difficult case is when we have parallel resistances. And parallel, if you've talked about voltage difference, parallel have the same voltage difference across them. For those of you that haven't had voltage difference yet, if I have a resistor like this,
parallel is providing an equivalent path off to the side. So that would be parallel. And I'm going to put over here, these are the two things that I'm going to connect a battery to or something. So I'm trying to get current going through there, coming out there, charge going in there, coming out there. Okay? Some of it's going to go this way, some of it's going to go this way. Just not even talking about voltage, if we talk about a difference, an energy difference in electrons between here and here, it's got to be the same energy difference between here and here. Because all we've got in here is conductors, wires. There's no resistance drop, there's no energy change. So if that's true, you could think whichever one has the bigger resistance is going to be the one that the charges are not going to want to go through. Okay? So suppose this is a gigantic resistance and this is really small resistance, like almost like a wire. Well, more charge is going to flow this way than that way, and vice versa. But really importantly, just adding another path for those charges to go through makes it easier to go through it. So if I start with one resistor, R1, and then I add another path, some charge can go this way now. Well, that's good. That decreases the resistance, right? I mean, depending on what we want. If we want more resistance, that's not great, but it decreases the resistance. Think of this. You're driving down the road and there's a backup. Okay, it's kind of hard. Not many cars are getting through the intersection. Oh, but wait, here's this right-hand turn. I can go around the whole thing. So more traffic can flow because we have more alternate paths.
So notice what happens to the current in the circuit when I connect that other one. It provides another path. So the current through the right resistor remains the same, but we're adding an ability for current to get from one end of the battery to the other through this other resistor. So it ends up being a parallel path, decreases the effective resistance that the battery sees because there are two paths.
And we call that parallel. Let me call that R2. This is parallel. And parallel doesn't mean those resistors are parallel to each other. We could draw these a bunch of different ways. I'm going to show you that. Parallel means the opposite ends are connected together. Here's one end of R2, here's one end of R1. They're connected together. The opposite ends are also connected together. We like to draw them like that. It looks parallel, but I could draw it like this. If this is the circuit I'm looking at, I could draw them like this. That's parallel. The opposite ends are connected together. Again, this is just a wire. So it's exactly the same as this end is connected to that end, and this other end is connected to that other end. That's parallel. In fact, this is parallel, right? The opposite ends are connected together. This is, again, just one big wire. So when you have parallel resistors, and we can prove this if we assume we know Ohm's law. I'm going to prove that separately when we get to Ohm's law. But if we have parallel resistances, the equation is this: 1 over R parallel equals 1 over R1 plus 1 over R2 if we have two resistors. Really, the equation is 1 over R parallel is equal to the sum of 1 over Ri for however many resistors you have. In other words, I could have many resistors in parallel. And I don't have to draw it like that. I could draw it like that, you know. When you get these things hooked up with wires, man, it might not look like this, right? It might not look like this. We'd have wires coming around, connection. But as long as the alternate sides of the resistors are all connected together. One side of each of these is connected to this piece of metal, this wire. The other sides are all connected together. These two are not parallel right now because this end is not connected to that end of that resistor. Now, notice this. This is on the bottom. So if you plug in all your resistors, and let me show you a real easy way to do this, is if I had two parallel resistors, and let's just say this is 100 ohms and this is 20 ohms. If I just go turn this on and I go 20x to the minus 1 plus 100x to the minus 1 equals, and I get 0.06. That's not the resistance. That's 1 over the resistance. So I go answer to the negative 1, and I get 16.66 is my equivalent resistance. And that means what I can do is if I had a circuit with this, I could just replace it with 116.6 bar ohm, I really should have units, resistor. That is my equivalent resistor using the formula for parallel. Again, what I did was 1 over 20, 1 over x, plus 100, 1 over x, and then equals, then I did 1 over x, and I got that. Notice it's smaller. It's easier for charge to get through this whole part of the circuit if you have two different places they can go. So that's parallel and series resistance. And you can do combinations. Last thing I'm going to talk about here is you can do combinations. Remember that ugly thing that I had on the board earlier? I'm going to do this pretty quickly. Okay, and when you do combinations, what you want to do is pick something you know, solve it, redraw the circuit. So let's just do this one. Let's say this is 4 ohms. I'm going to leave out the units. This is 2 ohms. This is 5 ohms. This is 10 ohms. Okay, I'm going to leave out the units just so it's a little clearer. Well, let's see, do we have any parallel or series resistances? Well, this is not in parallel with this because these two ends aren't connected. It's not in series with this because there's some other connection there. So it's not like whatever goes through this has to go through that. Same here. These look like maybe they're in series, but then there's this coming off. Okay, but look at this. These two are in parallel. How do I know? Because the opposite ends are connected together. So what I can do is I can redraw that circuit, but replace that with one equivalent resistance using the lesson for parallel. 1 over Rp equals 1 over R1 plus 1 over R2. So I do that, and once again, it's really pretty easy to do. 2 times 2x to the negative 1 plus 4x to the negative 1 equals, then I do x to the negative 1, and I get 1.3 bar ohms. Well, look, these two are now in series. Whatever goes through this goes through this. 5 plus 1.3 bar. I can actually now replace those with a new equivalent. That is 5 plus 1.3, 5 plus 1.3 bar ohms. Now look, these two are in parallel. So I can do one more step and reduce that to an equivalent. And when I do that, I end up with 1/10 plus 1 over 6.3 bar. Whoops, let me do that. I'm sure this is exciting watching somebody punch stuff into a calculator. And then I do 1 over that, and I got 3.88. Now I'll put ohms, put the unit. So the resistance between these 2 points, how hard it is to push charge through here, in here, and out here. Look how ugly that is, and yet by doing several steps, actually 3 steps because I left one out, I end up with one equivalent resistance. So that's how you do equivalent resistance using parallel and series resistance equations. There are going to be some. There are some structures that you can't really do it that way, but for everything in my class, you can always just start, think of it like a puzzle. What do we find if there are any series ones? Find if there are any parallel, reduce those, replace them by equivalents, and then just keep working over.